Hello again, everyone. This is Mr. V. Hill, and today we're going to talk about algebraic expressions and the coordinate plane. This will mostly be a review for most everybody, but it'll go quick for you, and just pay attention, and we'll talk about this a little bit, starting with the coordinate plane. You've all seen this before. Basically, the coordinate plane consists of two perpendicular number lines. The horizontal number line we call the x-axis, and the vertical number line we call the y-axis. And these are number lines, so every point on this line is given a name, just like the regular old real number line. Same thing with the y-axis. And so any point out in this entire plane, this two-dimensional flat space, is given a name of an ordered pair. So for instance, if we had this point right here, we notice that directly below this point, well, this point on the x-axis number line, we already gave that point the name of 1. Directly to the left over here on the y-axis, we gave that point a name of 3. So this point right here is going to be named with the x-coordinate first, 1, and then the y-coordinate second, 3. And we write this as an ordered pair, 1, 3. And since we've named every single point on this number line and every single point on this number line, using this technique, every single point in this plane is now going to have a name given by the x-coordinate and the y-coordinate, which will both be real numbers. And just to be clear again, the real numbers are all of the rational numbers plus all of the irrationals. Not just the irrationals. A lot of people messed that up on the last quiz. A couple other things here. For instance, here at this point, the point 0, 0, where the two axes meet, where they intersect, it's also said. That point is, of course, called the origin. The point 0, 0. The two axes divide up the plane into 4 quadrants. This we call the first quadrant, labeling it with a Roman numeral 1. This is the second quadrant. This is the third quadrant down here. And this is the fourth quadrant down here. And you might be asking yourself, oh, okay, so that's cool, but why in the world do we name them this way instead of just labeling them left to right, top to bottom like we do with everything else, like how we read English and whatnot? And well, that's a pretty darn good question. And I think if you're really curious about it, that'd be a good thing to ask about in class. I'm not going to get into that right now. Well, yeah, just because. But that's the idea. That's pretty much a review for you. I think you guys all understand that. But now what I want to look at is how are we going to make use of this coordinate plane for what we're going to be doing in Algebra 1. And that's where we get into our algebraic expressions. So back when we were doing sequences, which we just got done with, all our sequences we had things like a sub n was equal to 5 plus 2 times n, things like that for an arithmetic sequence, or a sub n is equal to 5 times 2 to the power of n for a geometric sequence, those kinds of things. So right here, these guys on the right are algebraic expressions. Algebraic expressions just being some combination of numbers, operators, and variables put together in some way that makes sense. Like you're not going to have minus 5x. That doesn't make any sense because what are you subtracting it from? It might be, well, turn into a negative. But anyways, we want to put these things together in some way that makes sense. And so now we're going to, instead of using n, because n means we're just referring to only natural numbers as numbers that can go in for n, we're going to switch up to x's and y's because that's the letter we use for our axes in the coordinate plane. So really simple here. Let's just start with something like an expression like 3x plus 2. Okay, this x is the variable. So x can be any real number whatsoever. That's how we normally use this. So an x refers to any real number. N just refers to any natural number. And so we could make a table of values here. X and 3x plus 2. We're going to be doing this a lot in class for the next activity. And we can let x be any real number, but we're going to keep it simple and just stick with integers for right now. Maybe just go -3, -2, -1, 0, 1, 2, and 3. And then for each of these values of x, this expression is going to give us a different value. So we just plug -3 in for x, and we have 3 times -3. Now, careful, when you plug this stuff in, we need to put the number that we're plugging in for x in parentheses. Right? So 3, it's not hugely important right now, but when we get to a little bit more complicated expressions, it's going to be. So 3 times -3 is, of course, -9. Add 2, we've got -7. -2, we'll plug that in. 3 times -2 plus 2, that gives us 3 times -2 is -6, plus 2 is -4. 3 times -1 plus 2 is, of course, -1. 3 times 0 plus 2, oops, I don't need that little parentheses right there, sorry, is equal to 2. 3 times 1 plus 2 is, of course, 5. And 3 times 2 plus 2 is, what do we got there, 8. And 3 times 3 plus 2 is equal to 11. Okay. So, now we've got x's, and now we've got these various values for this expression. So what we're going to do is we're going to really easily do something like this and just give this expression another name. How about y? We'll say that y is exactly what we get when we take 3 times x plus 2. Now we have an equation with 2 variables in it. 2 variables means, oh wow, we're back to that 2-dimensional space that we call the coordinate plane. So what we can really do here too is if we wanted to, we could turn these pairs into ordered pairs x, y. And so we end up with the point -3, -7, the point -2, -4, -1, -1, 0, 2, 1, 5, 2, 8, and finally 3, 11. And again, we could pick out different values for x. We could pick out rational numbers in between -3 and -2, pick pi, we could pick e, any real number we can put in for x, and that'll spit out a real number for y over here. And we put them together into ordered pairs. Now, we just graph these points, which we've done any number of times. So I'm just going to do a little sketch here. My x-axis, my y-axis, and we just plot the points. -3, -7, 0, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, right about there. -2, -4, -2, 1, 2, 3, 4, simple enough. -1, -1, that's right there. 0, 2, that's right there. 1, 5, right there. 2, 8, about right there. And 3, 11. 9, 10, 11. And of course, this is just free-handed, so it's not going to be perfect, but you kind of get the idea here. We can hopefully see that these points kind of line up in a straight line, and then we could think about connecting the points with a straight line and even extending that line on forever in both directions. Okay. So now, we've graphed these points, we've kind of filled in between them and extended the trend out in both directions. But the big thing to get out of this, because I'm sure you guys have all done this before, this thing, if we look at it as an equation, saying that y equals 3x plus 2, in the same way that we named each point on this number line with a number, we've named every point in this plane with an ordered pair. And now this equation is actually the name of the set of points that make up this line. So now, not only can we name individual points in this plane, we can name a collection of points, like this. The reason why this is a good name for this set of points is, well, if you plug in the coordinates, let's say here like 1, 5. If we plug the x-coordinate 1 in for the x variable here, and we take the y-coordinate and plug that in for the y variable here, we can just ask ourselves, plug in the 5 for the y, and we ask ourselves, is that actually equal to what we get when we take 3 times the x-coordinate of 1 plus 2? And of course, 3 times 1 is 3, add 2, we get 5. That's a true statement. Good. So that tells us that the point 1, 5 is on this line. It's one of the points that's on this collection of points. If we were to take something that's not on the line, like say down here, this point 3, 0 is obviously not on this line, we can ask ourselves, again, is it true that if we plug in this y-coordinate for y there, will it be equal to what we get when we plug in the x-coordinate over here? 3 plus 2. And we say 0, is that actually equal to 3 times 3 plus 2? Well, 3 times 3 plus 2 is 11. 0 is definitely not 11. So, no. So that tells us that the point 3, 0 is not in the collection of points that make up this line. So that's why this equation is actually a good name for this set of points. And that's pretty much all there is to it right now. And that's not the only way to think about these equations, but when we're looking at these equations as graphs in the coordinate plane, that's how we want to think about it, as this equation is just the name for this collection of points. All right, we'll talk about this a lot more in class. Hopefully you took some good notes. I'll give you a little practice next time we come into class. All right, thanks for watching.